Right, straight into this video, we're going to go through the definition of absolute convergence. So, a series from k equals p up to infinity of ak converges absolutely if the series from k equals p up to infinity of the modulus of ak converges. Okay, so that's the definition of absolute convergence. So if any of our terms are negative in the sequence ak, we take the positive and we sum all these up, right? So of course, if all the ak's are positive, then modulus ak is just the same, so this result clearly still holds. Anyway, one fact is that absolute convergence implies convergence. So essentially this means, but convergence does not imply absolute convergence. So absolute convergence is a stronger condition than convergence. So if we can prove something absolutely converges, we can have some nice properties. We're going to prove this statement. So we'll call this star and proof of star. Okay. So our assumption is that we have absolute convergence, and we need to show that that shows that AK converges. So we know that the partial sums, which is defined to be, or Sn is defined to be the partial sum of the modulus of the AKs, that tends to some S in the real numbers as n tends to infinity. That's just the definition of convergence. So if AK converges absolutely, we know that this is true. We also know that Sn is increasing. This is because Sn is the sequence of these sums, so as n increases we're adding on extra terms, but the modulus of AK is clearly greater than or equal to 0, so Sn is increasing, right? So Sn is less than or equal to S. Okay? Now we're going to define a new sequence. Xn is equal to the sum, the partial sum, equals p up to n of AK plus modulus AK. And this is increasing. Okay. And why is this? Well, AK can be negative, but AK can't be bigger in magnitude than the modulus of AK, clearly. So even if AK is negative, we add on the positive of AK with the same magnitude, so this sequence is always getting bigger and bigger and bigger. Okay, or at least non-decreasing. So therefore, well, not therefore, Xn though, we also know is less than or equal to the sum from k equals p to n of 2 AK. And why is this? Well, because if AK is positive, then this is equal to 2 modulus AK. But if AK is negative, then it's clearly going to be less than this. So in either case, an AK is either positive or negative, or 0, but 0 falls in the same category as positive in this sense. because 0 plus mod 0 is just 0, so we're fine. And then 2 times mod 0 is still 0, so it's in all three possible states that AK can be in. This holds, so it's true, and that's equal to 2 times the partial sums of Sn, which is less than or equal to 2s. Okay, because Sn is less than or equal to s. Therefore, Xn converges by what we call the monotone sequence theorem. And if you haven't seen that, I'll link that in the top corner. But essentially, because Xn is increasing and is bounded, it must converge. Okay, so now, so we say Xn converges to X as n tends to infinity. So if we consider the partial sums of AK from k equals p up to infinity, partial sums are from k equals p to n of AK, and this is clearly equal to Xn minus Sn, and we know from our results in the last video about convergent sequences that this tends to x minus s as n tends to infinity. So again, I'll link that video too. So AK from k equals p up to infinity converges. Brilliant. So that's what we wanted to prove. If you don't understand any aspects of this proof, let me know down in the comments. But for now, that's it. If you did enjoy this video, please be sure to like and subscribe, and I hope to see you in the next one.